Hi everyone, let's talk about some of the mathematical formalism that underpins waveguides. Now to this point, we should be pretty comfortable with the parallel plate waveguide. We derived pretty straightforward mathematical expressions for the TE and the TM polarizations. And it was a little hectic, but the mathematics did lead to pretty tractable results. You got to be a little careful. It's easy to make a few mistakes, but when you slog through it, you get, something that's relatively interesting and easy to manage. If, however, we expand ourselves to the rectangular waveguide, a lot of those ideas are going to be preserved, but the mathematics is going to get extra cumbersome due to that added dimension. So what we need to do is step back for a moment and think about what exactly it is we're trying to calculate here, and what sort of simplifying assumptions can we introduce into the fields here to create a tractable problem. So you notice here I have written down some of the general expressions that we are interested in whenever we deal with waveguides. So in particular, we have the electric field here and the magnetic field here, which I've written out in kind of its full glory, right? So normally we think of this as just a field that is a function of x, y, and z, but each vector component is itself going to be a scalar field throughout all of space. And same thing for the magnetic field. You have an x, y, and a z component, and each component is this nasty scalar field unto itself. And we don't normally think about this because we usually bottle all of this up and squish it into this nice compact notation. And in fact, moving forward, you will see me periodically even squish it up even more using this kind of notation here. So, h of r, right? So that x, y, and z can be thought of as a position vector. Now, whatever these solutions are for these fields, they also have to satisfy Maxwell's equations here. So I have Faraday's law and Ampere's law, which in turn imply these two Helmholtz equations. So what we need to do is take a step back and think about what are we trying to solve so that these expressions become tractable for the rectangular waveguide. And then we'll be able to use some of that formalism when we move on to, say, the circular waveguide or the coaxial waveguide. So with all that in mind, let's start with our first major assumption. Whenever you hear the word waveguide, in particular, the rectangular waveguide is what we're after right now, this is going to imply a very specific form of my solution. That is, all of my z dependence is going to be wrapped up into this complex exponential representing some kind of phase propagation down the positive z direction. So whatever these functions are, and across all of these vector components, the z dependence is going to follow this here. So you notice that immediately introduces a slight simplification, and it's going to look like this. So I'm going to write E of r, so x, y, and z, is going to look like the following. I'm going to write x hat E sub x as a function of x comma y. So this little e sub x, I've taken out the z dependence here. So it still represents this piece of the vector field here, just without the z. So that's what the little e is representing. So plus y hat e sub y of x comma y plus z hat e sub z of x comma y. And then all of this will just have this z dependence that looks like that. So you notice that the function of z has been removed and factored out over here. So every time I have a waveguide, this is kind of the general form of the solution I can assume, or that I'm looking for. And of course, the same thing will apply to my magnetic fields. You will get x hat times a little h sub x of x comma y plus dot 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 z hat h z x comma y, and then there'll be this thing here. Okay, so that is a good step in the right direction, right? Because you see how it's removed an entire sort of dependence on all these scalars and made it consistent out here and factored. So now we're also going, for the sake of argument, let us assume a very specific polarization, transverse electric polarization for my wave. And this means my E sub z is equal to 0. Now, again, this might feel like sort of a wild assumption at first, but we have the benefit of hindsight in that this will lead to a tractable solution for my waveguide, which means once I have a solution, it is a perfectly acceptable solution. So we're going to make this sort of, quote unquote assumption here, knowing that it will take us somewhere interesting. Likewise, if we had done transverse magnetic, that would have imposed the condition that this H here is 0. So we're going to focus just on the transverse electric. And of course, all of the mathematics will be perfectly paralleled, whether we make the one assumption or the other. These are just totally orthogonal systems here. So for the sake of argument, let's stick with the TE. And then the TM just sort of follows all of the same results. And you can skip all the details when you go back to there. So the reason we do that is it allows us to basically set this guy to 0. Now, it also gave us another interesting result that if we made this particular assumption here, so let's just go ahead and write this out, h sub y of x comma y. In class, we did sort of a short quiz where we also found that if we made this assumption on the magnetic field and we impose a kind of a Helmholtz equation here, we get a very useful result. And we found that the Helmholtz equation acting on the z component here required the following condition. H sub z. So the partial with respect to x plus the partial with respect to y acting on this little term here, plus, then we had a k naught squared minus beta squared. So when I say k naught over here, I mean k naught is equal to omega divided by the speed of light in vacuum. And this was h sub z equals 0. So remember, we proved this in class, that if we made this assumption on the magnetic field and it satisfies a Helmholtz equation, this little expression here has to be true. So it's not obvious right off the bat why this is helpful, but you'll notice instead of a 3-dimensional, so make a note up here, this is a 3-dimensional sort of equation here. It's got a vector with this Laplacian acting on everything, but when I made this little assumption by pulling out the z's, I got this little result here, which is only 2-dimensional. I just have a partial with respect to x and a partial with respect to y. And then this particular term here, we're going to call k sub c. That's in your textbook. So the reason why this is interesting is it turns out that if I can solve for h sub z, every other one of these little scalar fields is going to follow. So you can, in a sense, you can treat this almost like, sort of like an independent variable. Well, it's not really a variable, more like a function. Independent. And then all these other guys up here will be dependent. So again, the idea for this is going to be when I calculate the solution for this particular field component, my longitudinal, it's not arbitrary, I'm picking the one that is longitudinal down the waveguide. When I have a solution here, I will then immediately be able to calculate each and every one of these other pieces as a result. So that is what we're going to do with the rest of this sort of derivation, is show how to calculate all of these little individual fields here, presuming I have this calculation in hand, right? Because remember, h sub z is equal to little h sub z times e to the minus j beta z, where this guy is a function of x and y. So if I know what my little h sub z is, then I can actually calculate the big H and all of these other terms here, or equivalently all of these, and you just tag on the little e to the j beta z. So that is our goal. I need to kind of start here. If I can solve this, calculate these other functions here. Okay, so with all that in mind, let's assume, hypothetically, this guy here, let's draw this out here. Let's just assume this is known. Like somehow I have figured out a solution for this field here by calculating this solution for this big equation here. What then are these other 4 field components? Well, the answer is actually pretty straightforward. It's going to be a little tedious, but there's nothing terribly difficult. It's just a bunch of derivatives. So I'm going to express everything as a function of h sub z. So first things first, recall Faraday's law. Del cross E is negative j omega mu naught times h. So that may look like one equation, but it's actually 3 equations in one. And they look like the following. Partial e sub z with respect to y minus partial e sub y with respect to z is equal to minus j omega mu naught h sub x. So this is the x component of these guys being matched here. So you carry out the curl, you pull out the x component, you get this guy here, and then I pull out the x component of my h. Okay, so this is going to get a little tedious, so just bear with me. So partial e sub x with respect to z minus partial e sub z with respect to x is equal to minus j omega mu naught h sub y. And then we repeat again for the z. So partial e sub y with respect to x minus partial e sub x with respect to y is equal to negative j omega mu naught h sub z. Now, because of our assumptions, we've assumed the TE polarization and we had that e to the j beta z dependence. So what that immediately implies, first things first, this guy is 0, my e sub z. So we'll write that out. E sub z is equal to 0. Also, any partial derivative with respect to z is going to be replaced with a negative j beta. Because again, we have assumed that all of my z dependencies are separable with this form. So that becomes a j beta. That becomes a j beta. This becomes 0. And then this guy will remain the same. So let's do a quick little rewrite as the following here. We'll just say negative j omega mu naught h sub x is going to be equal to, so negative times a negative, plus j beta e sub y. So you notice some simplifications are starting to fall out, which is a good sign. J omega mu naught h sub y is equal to negative j beta e sub x, right? So replace the z derivative with that j beta, and this term went away. And then, of course, negative j omega mu naught h sub z doesn't change. So I still have that partial e y with respect to x minus partial e sub x with respect to y. So now we have to do the exact same thing with Ampere's law, okay? And so that's going to be a little tedious, so I'm just going to kind of skip to the end. So remember, Ampere's law, del cross h is equal to j omega epsilon naught times e. So this is going to imply 2 equations now. J omega epsilon naught e sub x is equal to partial h sub z with respect to y plus then partial hy with respect to z is going, is technically going to be negative partial h sub y with respect to z, but that's going to simplify real quick. Partial h sub z with respect to y plus j beta h sub y. So I just made the little substitution here. And then I'm going to get a j omega epsilon naught e sub y is equal to, just kind of skipping to the end, j beta h sub x minus the partial derivative of h sub z with respect to x. And then, of course, e sub z is 0, so I'm not even going to worry about that last term. So why did I do that? So I have 1, 2, 3, 4, 5 equations here. And what I want to do is kind of rewrite everything in terms of my h sub z. So I'm assuming, say, that I know what my h sub z is. Can I calculate all the other terms? And so what you do is just a bunch of cross substitution, okay? So you notice I have this e sub x here. That is going to get substituted over to here. Then my e sub y gets substituted into here. And you do a little bit of mixing and matching. And we end up with the following set of equations. H sub x is equal to negative j beta over k sub c squared times partial h sub z with respect to x. And then we get an h sub y is equal to negative j beta over k sub c squared times partial h sub z with respect to y. And I gotta be careful here. So then my e sub x. So again, please bear with me. This is a little tedious, but this is just one of those things you have to do in electromagnetics sometimes. Just keep track of all these little vector components. And partial h sub z with respect to y. And then e sub y is equal to j omega mu naught k sub c squared partial h sub z with respect to x. So these are the equations I am after. So you notice the idea behind this is essentially given h sub z, find everything else. So that is the sort of the philosophy here, right? I have this little equation here, this two-dimensional Helmholtz equation for my little h sub z, which then tells me my big H, because I just have that little dependence there. And then once I have this guy, it's just a bunch of scalar multiplications and some partial derivatives to get all the other field components. So the way to think of this is my longitudinal vector down the waveguide, the field component that points in the direction of propagation. Think of it as kind of like an anchor for the entire solution of this system. Okay, so again, I have one equation I need to solve, one giant partial differential equation here in 2 dimensions. So we're going to solve this guy here, and then once we have the solution here, I can derive all the other bits. So that, again, it's like this anchor that from which all the other field components are derived if I know this particular field component. So that is the formalism we're going to exploit when we derive the solution for the rectangular waveguide.